In this lecture, we are going to see one of the methods of finding the forces in the members of the truss, that is the methods of joints. In the previous class, we had introduced the concept of the truss, and we had seen that what is the need of the truss and why it is important for us to determine the forces in all the members of the truss. Because for the proper designing of the truss, we must be aware of the forces which are present in all the members of the truss. So actually there are two methods of finding the forces in the members of the truss. The first method is the method of joints and the second method is the method of sections. In this lecture, we will restrict our discussion to the methods of joints. That is, we will see how we use the method of the joints for finding the forces in all the members of the truss. So there are various steps which we have to see while we are using the method of joints. So step number one, draw the free body diagram of the whole truss, assuming it to be a rigid body. Okay, we will assume that whole truss is a rigid body, and we can find the support reactions using the equilibrium equations, summation of the forces in the x direction to be 0. Similarly, the summation of the forces in the y direction to be 0 and summation of the moments about any point to be 0. So these three equations give us the condition of the equilibrium for a planar rigid body. Okay, so actually there can be a planar truss, there can be a space truss. Space truss means the three-dimensional truss. But in our course, we will restrict our discussion to the planar trusses. Therefore, for the planar trusses, we need only three equilibrium equations, that is two force equations and one moment equation. Therefore, it says that assume the truss to be a rigid body. The planar truss can be assumed to be a rigid body. And after drawing the free body diagram, we can use the three equations to find out the support reactions. See one more thing. We can have the truss is usually supported at 2 points. Okay, the truss will be supported at 2 points. One support you can see in the questions, it will be usually a hinge support, and another support will be a roller support. So in the case of the roller support, we have one reaction, and in the case of the hinge support, we have two reactions. So combining them, we will have three reactions, and those three unknown reactions can be easily found out by using these three equilibrium equations. But sometimes in the questions, you can see that there are two hinge supports. Okay, both the supports are the hinge supports. So in that case, we will have four reactions, two at each hinge. So in that case, it won't be possible for us to find all these four hinge reactions. Okay, all the four support reactions can't be found out by using these three equations. Okay, so it depends upon the question whether we have two hinge supports or we have a hinge support and the roller support. Now see the second step, draw forces in all the members, assuming the force in all the members to be tensile. Okay, we have to show the force in each of the members, and we have to initially assume that the forces in all the members is tensile. Okay, that is, it is trying to stretch the member. Okay, we had seen in the previous class how is the tension force and how is this compression force. Okay, these two things we had seen. Now see here, select a joint with maximum two unknown forces and use the equilibrium equations, summation of the forces in the x direction to be 0 and summation of the forces in the y direction to be 0. After that, we have to select a joint where there are at max two unknown forces, because joint can be considered to be a particle. Joint is not a rigid body, it can be considered to be a particle. And for the equilibrium of the particle, we can use only two equations, that is two force equations in the x direction and the y direction. Therefore, the step third becomes that select the joint with at max two unknown forces and use the equilibrium equations, that is two force equations. After that, we can see that once we use the equilibrium equation, if the forces come out to be positive, then our assumed direction is correct. That is, the members will be in tension. And if the forces come out to be negative, then our assumed direction is wrong. Okay, because I told you that initially we will always assume that the members are in tension. If our result comes out to be positive, then we can say that the member is in tension, that is, our assumed direction is correct. However, if it comes out to be negative, then the member actually will be in compression, that is, our initial direction of the tension that we had assumed is wrong. So similarly, you can see that in the second step number 4, select the next joint, and so on. Okay, we will go on selecting the joints until and unless all the forces are known to us. Okay, so let's see one example here. There is a planar truss given here. You can see in this figure there is a planar truss. We can see that there are 5 members. That is, the number of members are 5, 1, 2, 3, 4, 5. And there are, I think, 1, 2, 3, and 4 joints. Okay, you can see that there are 4 joints. So for the stability of the truss, we had seen that the number of members should be equal to 2g minus 3. So that means 5 should be equal to 2 into 4 minus 3, that is 8 minus 3, which is equal to 5. Therefore, we can conclude that this truss is a stable truss. So what we had to initially, the first step was that draw the free body diagram of the complete truss. Okay, draw the free body diagram of the complete truss. So for the free body diagram, we have to remove these supports, and in place of the supports, we have to introduce the support reactions. Okay, so this is a hinge support. Therefore, we will have one reaction in the vertical direction and another reaction in the horizontal direction. Okay, again, these reactions are not, the directions are also not known to us, but we can initially assume any direction. And if the result comes out to be negative, then our initial assumption is incorrect. It has to be in the opposite direction. Okay, so this is AX. Now here is a roller support. This was a hinge support. Now there is a roller support. Therefore, we will have only one reaction. This is by. Okay, so once we have found all once we have drawn the free body diagram, the reactions has to be determined. Okay, those reactions can be determined by applying the equations of the equilibrium of a rigid body on the stress. So for first equation will be summation of the forces in the x direction should be equal to 0. Okay, so here it will imply that ax is equal to 0. Similarly, summation of the forces in the y direction should also be equal to 0, which gives us that ay plus by, that should be equal to p. This is our second equation. Now, the third equation will be a moment equation. We can take the moments about any point to be 0. So let's suppose that we are taking the summation of the moments about A to be 0. Okay, suppose if this is the distance x and this is the distance y, then I can say that P will create a clockwise moment about A whose magnitude will be equal to Px, and B will create an anticlockwise moment about A whose magnitude will be equal to so suppose this is our third equation. Okay, so with the help of these three equations, we can find out the support reactions. Okay, we can find out the support reactions. Now see, after this, what we have to assume? We have to assume that all the members, okay, the forces in all the members are tensile. Initially, we will assume that forces in all the members are tensile. We can assume the forces in all the members to be compressive. We can assume the forces in some members to be tensile and some members to be compressive. But it is usually accepted to, as far as the textbooks are concerned, they usually assume, okay, it is a standard practice now that assume the forces to be tensile. Okay, initially assume all the forces to be tensile. Okay, there is no restriction, but it has become a habit that we usually assume the forces in all the members to be tensile. Okay, so let me take an example of this member DC. Okay, if I take the example of this member DC, this is D, this is C. Okay, so I have to assume that this member is in tension. Then the force on this member will be Fcd. That is, this is the way how we show the force on this member. Okay, this means that that is this member is in tension. Okay, this means that DC is in tension. Compression we would have shown in the opposite direction. Okay, compression we would have shown in the opposite direction. Okay, that would have been pointing inwards. Okay, so if I'm showing the compressive now, then the compressive force will be shown by this direction. Okay, this means that member is in compression. The member is in compression. Okay, so initially, but we have to assume all the members to be in tension. So let's move to the next slide. Again, introducing this image. Let me focus again on this DC member. This is D, this is C. This is the force in the member DC. Okay, this shows the force in the member DC. And initially we assume this to be tensile. Okay, this is how a tensile force is shown here. Okay, now let me show this member DA. Okay, let me show this member DA. Again, I want to show that the forces in this member DA are tensile. Then the forces on this member can be shown in this direction. That is, again, I am saying that AD is in tension. Okay. Now see here for the equilibrium. Okay, what we have this member and a joint D. Okay, we have this member DC and a joint D. So if I am showing this force here in this direction on this member in this direction, then on the joint, the force should be in the opposite direction. Okay, from the Newton's third law. Okay, these forces will be equal, but they will be opposite. Okay, so therefore, again, if I'm showing this DC here, okay, this is DC, and here I'm showing the joint D. If force in DC member is shown in this direction, okay, if force in member DC is shown in this direction, then the force in the joint will be same, but it will be in the opposite direction. That is if this is FDC, okay, this is FDC. Similarly, what was connected with this joint D, the member DA was connected with this joint D. So if this is the member DA, if this is the member DA, and we had assumed our direction to be tensile, if this is FAD, okay, if we are showing this member AD and the force is acting in this direction, then on the joint, as per the Newton's second law, it will be, for the joint, it has to be shown in the opposite direction. Okay, for the equilibrium, it has to be shown in the opposite direction. Okay, so this way, similarly, we can see if we see this joint here, C, okay, we can see this joint C. One more thing you can see that the forces in the joints, if the member is in tension, okay, if the member is in tension, then the forces in the joints will always be away from the joint. Okay, you can directly take this member. After understanding this concept, you can always initially assume that the forces in the joints are away from the members. Okay, you can see that here clearly. This FDC is away from the joint. If I have assumed this FDC member to be in tension, then on the joint D, I have to show the FDC away from the joint. Similarly, I am assuming that AD is in tension. Therefore, this will be the direction of force AD in the member, and the direction of the force AD on the joint will be away from the joint. So following the same steps, we can see that if I take the example of the joint C, okay, so joint C is connected by these members. One is the member DC, Another is the member CB. Okay, you can see that another member is member CB. And another member is member AC. So if I'm assuming AC to be tensile initially, then FAC will be in this direction and FBC will be in this direction and FDC will be in this direction. Okay, so to show the forces on the joint C, let me show it here. If this is the joint C, what will be the forces? FDC is towards it, then on the joint we have to show FDC away. Similarly, FAC is towards the joint, but on the joint it will be shown away from the joint. That is, this is FAC. Similarly, FBC, okay, towards the joint, okay, if I am assuming this to be the joint, then on the joint it will be shown away from the joint. And we also have some applied force P, which is acting here in the vertically downward direction. Okay, so the simple case is that you can directly, without drawing these figures, okay, without drawing these FPDs of the members, we can directly see if I want to write the if I want to see what are the forces on this joint, I can directly show that this is the joint C. There will be one force in the member AC. Okay, there is a member AC connected to this joint. The force in the member is tensile. Therefore, on the joint, I have to show it away from the joint. On the joint, I will show it away from the joint. FDC, okay, FDC. On the joint, I will show that this force is away from the joint. And similarly, FBC, then on the joint, I will show it that it is away from the joint. But remember that these directions may be correct or they may be incorrect depending upon whether the forces obtained after the analysis is positive or negative. Okay, if it comes out to be positive, then our assumed directions are correct. But if it comes out to be negative, then our assumed directions are incorrect. Okay, so similarly, if you want to draw the free body diagram of the joint B, we can directly see that if this is the joint B, there will be one roller reaction. This was By. Now it is connected to two members, BC, okay, BC member. Then the force in the BC member on the joint will be shown away from the joint. And the force on AB member, again, it will be shown away from the joint on the joint B. Similarly, if I want to draw the free body diagram of this joint A, if this is joint A, for joint A, FAB will be away, FAC will also be away. Okay, all these initially are assumed to be away from the joint. FAD will also be away. And I had these two support reactions which I had assumed to be AX and AY. Okay, so once we have drawn the free body diagrams of all the joints, okay, we don't need to draw the free body diagrams of all these joints. We have to select the joint which has the where at max two unknowns are there. Okay, so initially I could have started with the joint number D because here there will be only two unknowns. See here, joint number D is where, okay, this is the joint number D. There are only two unknowns, DC and AD. So if there are only two unknowns, then I can use the two equilibrium equations and I can get the value of FDC and FAD. And so on, I will go on to looking where there are only two unknowns and I will use the equilibrium equations on those joints. Okay, so this all will be clear from the examples which will be follow now. Now let's see an example here. Okay, it's a very simple truss consisting of 3 members and 3 joints. Okay, so first of all, let's look at the stability of the truss. We can see that here the members are equal to 3. The joints are also equal to 3, 1, 2, and 3. There are 3 joints. So for stability, what should we have? M is equal to 2j minus 3. That is 3 should be equal to 2 into joints are 3 minus 3. And 6 minus 3 is also equal to 3. That is, the truss given here is a stable truss. Okay. Now, the first step for us is to find out the support reactions. Okay. So we can see here, there is a hinge support here, and this is a roller support here. Okay. The support is a roller. So we'll have 1 reaction here and 2 reactions at support A. Therefore, we will have 3 reactions, and we can use the equilibrium of a rigid body. That is, for that we have 3 equations. We can find out the support reactions. Okay. So let's first of all draw the free body diagram of the truss, assuming the truss to be a rigid body. Okay. So this is the truss. Okay, for the free body diagram, we have to remove the supports. Okay, this will be A and this will be C. Now, the external forces that are acting on this rigid body are, this will be 500 Newton, which is an applied force, and there will be 2 reactions. In fact, 3 reactions. 1 reaction will be at the roller support, that is equal to Cy. And at the hinge, we will also have 2 more reactions, one in the vertical direction and one in the horizontal direction. Let's say that this is equal to Ay and Ax. Let me assume the direction of the Ax to be, okay, I can get sense that this 500 Newton is in the positive direction. Then I can directly show that Ax is in the negative direction. Okay. Now we can use the 3 equations, that is summation of the forces in the x direction to be 0. And this gives us 500 is in the positive x direction and Ax is in the negative x direction. This has to be 0, which means that Ax is equal to 500 Newton. So we have found out the first reaction. Now let's find out the second reaction. The second equation that we can use is summation of forces in the y direction to be 0. We can see that Ay is in the positive direction, Cy is again in the positive direction, and there is no force in the vertically downward direction. Therefore, their summation has to be equal to 0. After that, we can use the third equation, that is the summation of the moments about any point to be 0. Let me say that the moments about hinge A to be 0. Okay, this is A, and this is B. Because these 2 forces don't contribute to the moment, it is quite easy to take the moments about the hinge A to be 0. Therefore, we can see that Cy, this distance is 2, this distance is again 2. Cy will create an anti-clockwise moment about A, whose magnitude will be equal to 2 Cy. And 500 will create a clockwise moment about A. Therefore, it will have the opposite sign, 500 into 2. This has to be 0. 2 and 2 will cancel out. We will get that Cy is equal to 500 Newton. And since the Cy came out to be positive, therefore our assumed direction is correct. Okay, our assumed direction is correct. Its positive value indicates assumed direction is correct. Now, substituting the Cy in the equation second, we have that Ay plus Cy is equal to 0. Ay plus 500 should be equal to 0. From here we get that Ay is equal to minus 500. Now what does this indicate? It indicates that this negative sign indicates that our assumed direction of Ay is incorrect. It also gives us the indication that Ay should be in the vertically downward direction. Okay, this is the correct direction. Okay, this AY should be actually in the vertical downward direction. Therefore, instead of this, we can also write that AY is actually 500 newtons, but in the vertically downward direction. Okay, so once we have found out the support reactions, now let's go on to the joints. So we can see that if I take the example of joint A, okay, although there are four forces, but only two are unknown because AX and AY we have already calculated. Now the unknown forces are force in the member AB and force in the member AC. And our initial assumption will be that all the members are in tension, therefore all the forces will be shown away from the joint. So let me take an example of joint A. This is the joint A. So there were two forces, that is AX. Another was AY. Now see here, this AY was actually assumed to be in the upward direction, but its result came out to be negative. That is, it is actually in the vertical downward direction. There are two ways to see this. I can keep this direction as incorrect. But while I am keeping this direction as incorrect, then I have to assume that this AY is minus 500. Whenever I will write that AY in the equilibrium equation, I have to write that it is equal to minus 500. Okay, because I haven't corrected the direction here yet. Therefore, I have to take the negative sign as well. The other forces are AB and AC. And AB and AC initially will be assumed that they are acting away from the joint because we have assumed that all the members are in tension. So this will be the force in the member AC and this will be the force in member AB. Okay, now another way to represent the joint A, okay, I can show that another way to represent joint A, it was that if this is the joint A, this is FAC, this is FAB. Now here I could have assumed the correct direction. I could have shown the correct direction because AY is actually in the vertical downward direction. Then when I am writing it in the correct direction, then there is no need to carry this negative sign here, okay? And AX was here in this direction. So these are the two ways to represent. We can show either the correct direction, then the value has to be the positive value, or I can keep the incorrect direction, but I have to keep the negative value with it. Okay. So summation of the forces in the x direction should be equal to 0. At joint, we can use only two equations. Okay. Forces in the x and y direction because it is not a rigid body. This is joint A again here. Okay. This is again joint A. So we can see that force in the x direction, positive x direction is FAC, and in the negative direction it is AX. So this has to be 0. Then FAC is equal to AX, that is equal to 500. Now, since this FAC came out to be positive, it means that our assumed direction, that the tension, that the member AC is in tension is correct. Therefore, this member will be actually in tension. This member will be actually in tension because the result came out to be positive. Now, I can use that summation of the forces in the y direction has to be 0. Okay. So forces in the y direction are FAB. Okay. If I am using this here, FAB is in the upward direction. AY is also in the upward direction. So this has to be 0. The summation has to be 0. Now see here, I am showing this wrong direction. Therefore, I have to keep this AY to be negative. Okay, AY has to be minus 500 here. So FAB we have to find out plus AY is minus 500 here because I have shown the wrong direction here. If I had shown in the downward direction, then I had to show it to be the positive. Okay, but I have taken the wrong direction here. Therefore, I had to keep the negative sign with it. So this gives us that FAB is equal to 500 newtons. And again, this result is positive. That means that this member AB is also in tension. Okay, AB is in tension. We have found FAC, we have found FAB. Now we are only left with FBC. We can use both the joints B or C because at the joint B, we have only one unknown, that is BC. And as well as at the joint C, we have only one unknown, that is BC. Okay, because AB we have found out, AC we have found out. Let's take an example of joint C. So if this is joint C, then CY is acting in the upward direction. AC will be shown away from the joint because we got AC is positive, therefore it is in tension, therefore it will be definitely away from the joint. Here we have CY and this BC, force in the member BC can be shown away from the joint. This FBC can be resolved into two components. Since this angle is 45, so this will be FBC by root 2, and this component will also be FBC by root 2. So we can use the equilibrium equation. Suppose we are using the equilibrium equation in the y direction. Force in the y direction should be equal to 0. CY is also upwards and FBC by root 2 is also upwards. Therefore, we can write that FBC by root 2 plus CY is equal to 0. Then FBC will be equal to minus CY root 2. That is, it will be equal to CY here is 500. Okay, CY is 500 minus 500 root 2, and this is FBC is minus 701 Newton. So here we got the result to be negative. Since this result is negative, that is this BC is in compression. Our assumed direction that BC is in tension is wrong, but actually BC is in compression. So this was one example by which we can see how to use the method of joints. Let's have a look at this problem. So here we can see that there is a truss where 2 point loads are acting, and they are acting at the joint B and joint D. Okay, so the first step here is that we have to draw the free body diagram. So again, we can see that there is a roller support. Okay, this is a roller at A, and there is a hinge at A, at C. So since we have one roller support and one hinge support, therefore it is possible for us to find all the reactions. Okay, 3 reactions and 3 equations we have. Now we can draw the Fpd diagram. This is the Fpd of this truss, which has been assumed to be a rigid body. We can see that this is the reaction AY, and C is a hinge. Therefore, there will be 2 reactions, one in the horizontal direction, and it's quite obvious that if this 600 Newton is acting in the positive x direction, therefore the reaction should be in the negative x direction. But we can't say for CY and AY. Okay, initially we can't say for AY and CY. We can assume their directions to be upwards and negative, downwards. Okay, and once the results come out to be positive or negative, on the basis of that we can confirm whether our assumed directions were correct or not. So let's apply the equilibrium equations. We can see that summation of the forces in the x direction should be equal to 0, which gives us that minus Cx plus 600. This has to be 0, which gives us that 6x should be equal to 600 Newton. This is the first reaction. After that, we can apply the summation of the forces in the y direction to be 0. We can see that AY is positive because it is upwards, minus 400 minus CY, this has to be 0. We can see that AY is equal to CY plus 400. And this is another equation. To find out the third equation, we need to apply the moment reaction. It will be quite easy to apply the moment reaction about the hinge C because two reactions will not be contributing to the moment about the point C. So we can see here, AY will create a clockwise moment about C. Therefore, taking the clockwise moments to be negative, AY multiplied by the force arm, that is 6. This 400 will create an anti-clockwise moment about C, whose magnitude will be equal to 400 into 3, and 600 will again create a clockwise moment about C. Sorry, anti-clockwise moment about C, whose force arm will be equal to 600 into 4. Okay, this will be the magnitude of this moment. So from here we get that AY is equal to, this will be equal to 3600 divided by 6. This AY comes out to be 600 Newton. Again, this AY came out to be positive. Therefore, our assumption that AY is in the upward direction is correct. Okay, so this AY will be in the upward direction. Now we can substitute it here and we can find the value of CY. So 600 will be equal to CY plus 400. And again, CY came out to be positive. Therefore, our assumed direction that CY is in the downward direction, that is also correct. Now, the next step after finding out the reactions that we have to see, we have to assume all these members are in tension. Okay, initially we will assume all these members in tension, and after that we will select a joint which has at most two unknowns. Okay, at most two unknowns. So if we see this joint B here, okay, if we take the example of joint B, we can't take this joint B because there are three unknowns: AB, this BD, and BC. The forces in these members are unknown. Okay, we can't use this equation. We can't use this joint because we have only two equations. Now, if we come to this joint A, we can see that there are two unknowns. Okay, although there are three forces AY, AB, and AD, but AY is known to us. Therefore, there will be only two unknowns, and we can use two equations to find out those unknowns. So, taking the example of joint A, if this is joint A, we can see the forces on the joint A are the reaction AY, the force in the member AB, and the force in the member AD. So initially they will be away from the joints. That is, all the members are in tension initially. We are assuming them to be in tension. So this will be Fad. This will be Fab, and let's assume that this angle is equal to theta. Then this Fab can be resolved into two components. One will be Fab cos theta, and this vertical component will be Fab sin theta. So for joint A, if we apply the equations of the equilibrium, we can see summation of the forces in the y direction, that has to be 0. Fab sin theta, that is in the upward direction, plus AY is also in the upward direction, so this has to be 0. So from here we get that Fab sin theta, okay, sin theta can be calculated from this figure. The dimensions are given here. If this is theta, sin theta will be equal to, this will be 5, this is 4, it will be equal to 4 by 5. And AY will be, comes from the right hand side, it will be 600, that is minus 600. So from here we get that force in the member AB is equal to, this has to be minus 750 Newton. That is, force in the member AB is compressive. We can say that Fab is equal to 750, but it is of compressive nature. Okay. Now using the equilibrium equation in the x direction, this has to be 0. Now in the x direction we have two forces, Fad and Fab cos theta. Both are in the positive x direction, so they will add up. This has to be 0. So what we get from here is that FAB is actually in the opposite direction. Okay, FAB came out to be negative. Therefore, the actual direction of FAB isn't upwards. Okay, it is inclined but towards down. Okay, so actual direction of FAB is this. This is the actual direction of FAB. Okay, that is, this direction is wrong. Okay, this direction is wrong. FAB will be actually downwards. But let's keep this direction. Okay, let's keep this direction. Although we have assumed it to be this, let's move on with this direction. But what we have to do when we put this value of the FAB here, that has to be put in the negative value, because here we have assumed that the direction is this. Okay, incline upwards, but actually it is inclined downwards. So if I'm keeping this inclined upwards, then this FAB has to be given the negative value, that is minus 750. Okay, or I can change the direction, then I don't need to give the negative value. Now FAD is here plus FAB cos theta. FAB is equal to, I have to give minus 750 because I am continuing with this wrong direction. Cos theta from the same diagram can be found out. It is equal to base by hypotenuse. Okay, that is 3 by 5. So this has to be 0. So from here we get that FAD is equal to, it will be equal to 450 newtons. And this is a tensile member, because the force is positive, which means that our assumed direction, that is, we had assumed that AD is in tension, is correct. Therefore, FAD is 450 Newton, hence the member is in tension. After this, we have to move to some another joint. Let's take an example. Let's see if we are able to deal with the joint D. See here in the joint D, we have this force, it is known to us. Now FAD is also known to us. BD is not known, CD is again unknown. Therefore, there are two unknowns, and we can use the two equations to find out the forces in the members BD and CD. So let's see. This is the joint D. The forces will be, this is an applied force, 600 here. FAD. This is FCD. This is FPD. I just want to look once again. Okay, yes, this is FPD. Okay, so this FPD can be resolved into two more components, one along the x-axis and one along the y-axis. So this will be, if this is theta, this will be the sine component, that is FBD sine theta. And we will also have its cos component, that is, it is equal to FBD cos theta. Now let's apply the force equation in the x direction. Okay, we are making the analysis of joint D. Summation of the forces in the x direction should be equal to 0. So 600 is in the positive x direction, and AD we had found out that is, it is equal to 450. Okay, but it is in the negative direction. Therefore, 600 minus 450. Okay, this is 450 in the negative direction minus FPD cos theta. This has to be 0. Therefore, FBD cos theta from this diagram can be seen, it is equal to, so if I take this to be theta, then it will be equal to 3 by 5. Okay, this will be equal to 3 by 5. Okay, this is 5 again. This will be equal to 150. And FBD will be equal to 250. and this will be tensile since the result came out to be positive. Similarly, we can use the equilibrium equation in the y direction. Summation of the forces in the y direction, this has to be equal to 0. And we can see that in the y direction we have Fbd sine theta plus in the same direction we have Fcd. So this has to be 0. Fbd is equal to 250. Sine theta will be equal to 4 by 5 plus Fcd. That has to be 0. So from here we get that Fcd is equal to minus 200 Newton. Okay, that is this member is in compression. Okay, we got the negative value. That means this member is in compression. So we have got the forces in the members BD, CD, AD, AB. Okay, AB, AD, BD, and CD. Now we are left with the force in the member only BC. So for that we can take the joint C and see that at the joint C there will be a reaction downwards, reaction towards left. Force in the BC we can assume to be towards the the force on the joint, force in the member BC can be shown on the joint towards the left, and force in the member CD can be shown in the downward direction. So let's make the analysis of the joint C. If this is the joint C, we can see that CY was acting in the vertical downward direction, CX was acting in the negative direction, plus what we had here is force in the member CD. And I'm assuming that all the members are in tension, therefore this is the force in the member BC. So if we take a step back, we just got that force in the member CD is actually compressive. Okay, so this direction which I'm showing here is the wrong direction. Okay, since I'm showing the wrong direction, actually it is to be shown in the opposite direction. Okay, because I had initially assumed here CD, okay, CD to be for the joint C. Okay, we can see that, and this CD won't be in this direction. Okay, CD won't be in this direction because initially I'm assuming that all the members are in tension, but I had seen that the member CD is not in tension, it is in compression. Therefore, on the joint C, this can't be the direction of CD. The direction of CD should be opposite. But since I am following that, I am assuming all the members to be tensile and I am showing this wrong direction here. Therefore, I have to take the negative value of CD, that is minus 200. Because it is not the actual direction of CD, the CD is actually the upward direction. Okay, I could have shown that also in the upward direction, but that time I have to take the positive value of CD. But since I'm showing its wrong direction, therefore I can take it to be minus 200. Okay, it can be taken as minus 200. So CX, I think it was equal to 600. This was equal to 600. So if I make the summation of the forces in the X direction to be 0, I can see that minus FPC minus 600, this has to be 0. So from here, what I get is, I get that FBC is equal to minus 600. And this again says that the force in the member BC is tensile. Sorry, it is compressive. Because we got the negative value.